So this is natural functions part 2. I split this up into 2 parts because we're going to do the word problems today, and they're a little bit tougher, and it'll take a little bit of work, but what's nice is typically each problem, although it looks different, the word problem is different, it's actually done the same way. So we're going to talk about modeling with these natural functions, and so remember the natural functions, there's 2 of them. There's e to the x, the natural exponential function, and there's ln of x, the natural logarithmic function. And so the formula is given to you right here, and I'm going to write it to the right here. It's q of t, and typically we use q because it stands for quantity, because we're typically trying to model the quantity of something, is equal to q naught, which is going to be our initial value, and then you have this e to the kt. Remember, e is the natural number, so it's actually a number, 2.718 ... on and on forever and ever. So let me identify these different pieces for you. So q naught we call the initial value. Or starting value. And then k, it depends on what textbook you use. Sometimes they call it the relative growth / decay rate, depending on whether you're growing or decaying, or continuous growth or / decay rate. I like continuous, but it just depends on the problem. So it's going to be relative or continuous. So we can call this the relative growth. If it's growing, we'll say growth, and if it's decaying, getting less, we'll say decay rate. You could also, though, call this the continuous growth / decay rate. This number will turn out to be important from the point of view, it'll tell us sort of how quickly it's growing or decaying. Let's talk about the graphs of these two things, because there's obviously 2 graphs. You have a graph for growth and you have a graph for decay. And so let me draw the 2 graphs here. So here's my x and here's my y, and once I draw them, I guarantee that you can figure out which is which. Here's my x, here's my y. And so here's one graph. It has a horizontal asymptote at y equals 0, and that goes up towards infinity. And here's the second graph. It also has a horizontal asymptote along the x-axis. And one's growth and one's decay. So which one's which? Hopefully you're going to say this is growth, because if you read it from left to right, it goes up. And of course, this one is decay. And k tells us, this relative growth / decay rate tells us whether it's growth or decay. If it's growth, k is going to be positive. And if it's decay, k is going to be, and you can guess now, negative. And so it's nice. If you get a continuous growth rate to be negative, you know it's decaying. If your continuous growth rate is positive, you know it's growing. I really like to say continuous because I know that this number e pops out when you study growth at a continuous level. So instead of looking at it over a time interval like a year or a month, when you start looking at the very instant, how is it growing at that very instant, this number e pops out in a natural way. All right, so that's my little spiel, my little introduction to modeling with natural functions. Let's take a look at some problems. How are you going to use this formula to solve some problems? And we're going to do 2. And we're going to start here with number 1, and I'm going to highlight some things. And so we're going to solve the following problems using the natural exponential functions. Now, there are lots of ways to solve these problems. We're going to practice using these 2 tools. Our two tools are e to the x and ln of x. And we're going to practice this so you become comfortable with this sort of notation. And once you become comfortable with it, these problems become relatively simple. So in 2007, the world's population reached 6.7 billion, and it was increasing at 1.2% per year. Find the formula for the world's population in billions as a function of years since 2007. I'm going to start with this first one, A. And it's real simple. As soon as I realize it's a problem where I'm going to use these natural exponential functions. I'm going to pull out this formula, q of t equal to q naught e to the kt. This is sometimes called, if you want, the exponential function. Different textbooks do different things, but if you want to give it a name, we can say we pull out the exponential function to model this, if we want to attach a name to it. And some of the stuff we know, they give us q naught, so we don't have to worry about that. So we know q naught is equal to, it's the initial value, and so it starts at what, 6.7 billion. So we know it starts at 6.7, let's say. We can always infer that the output is going to be in billions. And so I can rewrite my formula, q of t equal to 6.7 e to the kt. So that's one thing I don't have to worry about anymore. I'm trying to find this formula, so the only thing I need to figure out is what is k? And this is what I'm looking for. I need to figure out k. If I find k, then I'll find the formula for the population. And we could even use, if you want, instead of using q, you could use p here. We'll stick with q since I started with q. But you could use p and p naught for population. You don't want to get stuck on a single letter. Of course, t is good for time. All right, so what I know is that after 1 year, this increases by 1.2%, because it's growing 1.2% per year. That means if you plug in 1, so 6.7 e, I have k here, and I plug in 1 year for t, so 1, I'm going to get 1.2% more than I started with. So how do I write down 1.2% of 6.7? So you take 6.7 and you multiply by 1, which is the whole part of 6.7, plus an additional 1.2%. So that's 0, 1, 2. If you multiply 6.7 by 1.012, you're going to get 1.2% more of 6.7. And now I can divide both sides by 6.7. So let's take out a different color here. So I want to solve for k. So I'll divide both sides by 6.7. Divide both sides by 6.7. 6.7s will actually cancel on both sides, which is nice. So I just have e to the k equal to 1.012. And I can solve for k because I can use the other natural function, which is the ln function. So I can ln both sides. Then the k will come down. That's a property of logarithms. The k will come down. And so I get k ln of e equal to ln of 1.012. And ln of e, of course, is the nice number of 1. So I basically have my answer now. I know my k value is ln of 1.012, so q of t, my population size, is equal to 6.7. E to the k, and k is ln of 1.012 t. So there's a formula that will model the population. So now, a couple questions. What does it mean if you plug in 2 for t? What if you want to find q of 2? Right? Well, 2 is the number of years after 2007. So this says basically in 2009, how many people would there be? 6.7 e to the ln of 1.012. And then you multiply the exponent by 2. And you could use your calculator to figure that out. Second idea. This can actually be rewritten because you know e to the ln of the anything is the anything. So if you think about this, it's important to notice that you can actually just think of this as an entity in itself. E to the ln of the anything is the anything. So you could rewrite this as being equal to 6.7, 1.012, and then there's still a t in the exponent. And this is 1.012 comes from e to the ln of the anything is the anything. And now this is actually a little bit easier to understand. I start at 6.7, and each year I'm going to multiply by this 1.012, where the 1 is the whole part, The 0.012 is the 1.2% growth per year. It's important, though, that you use these natural functions so you can get used to them. So this is the answer. Right? This is how the work should be done. If you just simply write this down without any work, and it actually says use the natural exponential functions, you will get very few points, because really the point of this problem is to try to get you comfortable using e's and ln's. All right, part B, let's take a look at it. So in B it says if the half-life of a radioactive substance is 6 years, then how long will it take for 40% of the substance to remain? Now this is on the back of the handout I gave you with the rules of the natural functions on them, so you can turn that over and actually do the work on there if you like. I'm just going to copy stuff down here. So part B, I know I'm going to use this the exponential function, so q of t is equal to q naught e to the kt. So it's just sort of like a tool. I pull it out, and then I have to fill in, if I can, q naught and k, and then use that to figure out how long it will take. Let me come back up here. How long it will take for 40% of the substance to remain. All right, so I know after 6 years that's its half-life. So understand the idea of half-life first. So let's talk about this. What does it mean to have a half-life? Right, this is the time for how much of the substance to decay, and hopefully you say half, or you can say it's a time for 50% of the substance to now remain. So slowly the substance sort of decays into other things, and it's a time for half of it to disappear. There's also what's called a doubling time. I'm not sure if there's a hyphen there. Let's put a hyphen there. There's a doubling time, and that's sort of the opposite of the half-life. Whereas we have growth, and so instead of decay, you have growth, and we call it the doubling time, and it's a time it takes for the substance to double. So if bacteria are growing or something, it might have a doubling time. Okay, q of t equals q naught e to the kt. So I start here, and I know the half-life is 6 years. That means I don't know what q naught is, but I know if I plug in 6 for t, it's going to equal half of the initial substance, or half of the initial value, if you like. So how do you write half the initial value? Well, 1/2 the initial value. So 1/2 times q naught, or q naught divided by 2. What's nice about this is that we don't know q naught, but it doesn't matter. When we go to solve for k, you simply divide both sides by q naught, and q naughts are going to cancel here, and q naughts are going to cancel there, and you're going to be left with e to the k times 6, all in the exponent, equals 1/2. And now I'm going to take out the other natural function, that ln function, and do that to both sides, because I know if I ln both sides, this can come down in front, because that's a property of logarithms. And so now I have k times 6 ln of e equals ln of 1/2. And ln of e is a nice number of 1, and so k is equal to ln of 1/2 all divided by 6. Perfect. So let's go and plug that back into our formula. So q of t equals, I have no idea what q naught is, so I just write q naught, and then e to the ln I have of 1/2 divided by 6 here, and still all times t in the exponent. All right, then I go and look back at the problem. So if you look at the handout, you can look at it, and it says how long will it take for 40% to remain? All right, so what you're going to do next is you're going to pretend like you know t. So you say, okay, I have q naught e ln of 1/2 divided by 6 here. Now I'm going to pretend that this t is not a variable, that it's actually fixed. It's actually the time it takes for 40% to remain. So what does it mean for 40% to remain? Well, you have your initial value, And over here, for 50% to remain, we multiplied by 1/2 or 0.5. So here, for 40% to remain, that's 0.4. So 0.4 times Q naught is 40% of the initial value. 40% remains. And again, the same thing's going to happen when you divide both sides by Q naught. They are going to cancel on this side, and they're going to cancel on that side. And so I'm going to be left with e to the ln of 1/2 divided by 6, still a t up there, equal to 0.4. And I have to bring that whole expression in the exponent down. So what am I going to do? I'm going to do what to both sides? I'm going to use that other natural function, the ln function, and apply it to both sides, because I know properties of ln's, this thing can now come down in front. So let's write down what we have. I have ln of 1/2 divided by 6, all times t, with an ln of e, equal to ln of 0.4. Now ln of e is 1, so I can just drop that off. And for this last expression here, I want to solve for t. I'm dividing by 6, so to move it over I multiply. And on top, I'm multiplying by ln of 1/2, so to move it over I'll divide. So t is going to equal. So I'm dividing by 6, to move it over I multiply, so 6 times ln of 0.4, and then divided by ln of 1/2. And I can check this on my calculator. So on my calculator, if you have your calculator, you can take it out just to see how long it actually is. I mean, this is my answer here, and this is in years, because the growth was well, let's make sure you actually got it right in years. So we come back to the original problem, and you can look. The half-life of the radioactive substance was 6 years. So down here, this is actually in years, so we can write years next to it. And then I can crunch this number on my calculator just to get an idea of how many years it actually is. So 6 ln of 0.4, then divided by ln, and I could put, if you want, 0.5 instead of writing 1 divided by 2. And I get about 7.93 years out. So I know it's going to take around 8 years for 40% of the substance to remain. But this is my answer. It did not say round, just said find the years, so this is the exact number of years. Notice in these two problems, one's a growth and one's a decay problem. So which one's a growth problem, which one's a decay? Hopefully you say A is growth, and then that means B here is decay. If in this problem you do ln of 1.012, you'll see that that value should be positive. So ln of 1.012 because it's growth. All right, so you get a positive 0.011, blah, blah, blah. Whereas down here, if you look at this K value, this continuous decay rate, it should be negative. So let's try it out. ln of 0.5 divided by 6. And you get out negative, and it should be negative because it's decaying. We know that that K value tells you whether it's growing or decaying. You can tell that out from the problem itself. Second thing, like we did before in the other one, you can get a better feel for what this actually represents if you're able to interpret what this means. All right, e to the ln of the anything is the anything. So I can rewrite this statement actually as q of t is equal to, I do not know the initial value, so q naught, but I know that this e to the ln of the anything is the anything, so I can kind of separate this if you want. You can take this 6 and put it underneath the t, and then I get this to be 1/2. You get e to the ln of 1/2 is 1/2, because e to the ln of anything is anything, all raised to the t, and that's divided by 6 up there. And that kind of makes sense, because we know after 6 years you get half the original substance. So if you put a 6 in here for t, this becomes a 1. So you get 1/2 of the original substance. If you wait another 6 years, so you put in a 12, you're going to get a half of the original substance, so a fourth, and so on. So now this formula really starts to, speak to me. But again, the point of the problem is to try to use these, get comfortable with these natural functions, and solving these types of problems.